Hello and welcome to our presentation. Today we will show you how we try to improve the assembly experience of the FabScan and what knowledge we gain through this process that you can apply in order to improve the assembly experience of other personal fabricated objects as well. So what is the FabScan? The FabScan is a personal fabricated object. People can print out the pieces that they need to assemble the FabScan 100. Then they assemble it and they can use it to scan objects and create 3D models of them. Later they can print physical copies out of these 3D models that they created. We found out that there are some problems going from step 1 to step 2. This is the assembly process. So let's take a look into the problems. What people currently use in order to assemble the FabScan is a web manual. This web manual consists of pictures and text. Let's take a look into two consequent pictures of this manual. In this picture you can see the housing that is used to house the motor that is used for the FabScan. In the next picture you see the motor housing again, but this time with 15 screws on it and cables going out of it and an object that has been inserted. This logical leap can lead to sequence errors, which means that people do something during the assembly that they should have done later or before. This causes frustration because they have to go many steps back to fix the problem. This also costs time, of course. What about this picture? Well, in this picture you see two connected pieces with each other. And you may think that this looks correct, but it is wrong. This piece has been inserted in the wrong side. The assemblers recognize their mistake only after they have gone through many steps. Again, they have to go back through the steps, fix it, and they lose time and they get frustrated. This is a piece orientation problem. What do you look in this picture? What do you see? Is this the same piece printed two times? No. These are two different pieces, but they look very similar. People will mistake them and make errors. This is the piece identification problem. So, while assembling the FabScan, we realized that these three problems get repeated all the time. We tried to improve the experience and solve these problems. In order to do this, we decided to apply hardware modifications in the pieces and also develop an interactive assembly assistant. Let's take a look at what hardware modifications we have done. To solve the piece orientation problem, we applied physical constraints in the connectors of the objects so that they can only be placed in the correct side. What about the piece identification problem? Well, first we applied physical constraints so that it can only be inserted in the correct side. But we found out during a user study with 8 users that users get frustrated because they feel like we have cheated them. They see two identical pieces, but they can't fit the one they mistakenly took into the correct position. Only after they realize that these are not the same pieces and they cannot fit them wrongly, they take the correct piece.
Are you sure that you want to close the application?
Excuse me. So, to solve this, we decided to apply aesthetical modifications into the pieces. We tried to make them distinguishable one from each other. For example, we inserted labels in them. But we were not satisfied with what we have done. Labels are not an elegant way to solve a design problem. And the FabScan still had too many screws and nuts, which caused frustration and increased the building time. We thought, how does hardware improve in good end-user products? Well, if you notice, hardware tends to become smaller and it consists of less visible pieces. So what we have done is we completely changed the design of the FabScan. You can see the new design in front of you. It's also in front in this picture. As you can see, it is smaller, it has less volume. It also has 40% less screws and uses 33% less material. how did we do this? I want to highlight some of our examples to show you how our thought process was. Here you can see the piece that was holding the camera and the laser of the previous design, and here the new one. So where is the camera going? Well, we have integrated it in the front piece of the exterior housing. We applied many similar modifications, and this is how we came to these impressive results. We also tried to improve the assembly experience. We found out during the user studies that people had difficulties pulling the cable out of this housing after they have inserted the motor into it. What have we done to solve it? We changed the opening and gave it a meander shape so that after you have inserted the motor into the housing, you can pull the cable from downside. So, did we succeed? We tested it and we found out in a user study with 10 users that the number of errors they did with an old FabScan design was 23, and with a cube, it doesn't grow more, it was only 4. We also wanted to improve the screwing experience. This may sound funny, I know, but it was a problem, trust me. So, the nut openings had a rectangular shape. That way they were falling down all the time. You had to hold the piece with one hand and try to insert the screw with the other hand. We thought that if we changed the shape of the openings and gave it a trapezoid shape, the opening would be able to hold the nut. This is true, but unfortunately now you need to apply more force to insert the nut into it. We asked our users what design do they prefer, and while they mentioned that it was the nut opening was holding the nut, they were unsatisfied due to the fact that they had to apply more force to insert it. In hindsight, we can say that this is a problem that depends a lot on the size of your hands and your fingers and the force you are able to apply with them. So we should have tested with a larger user base to reach a clear conclusion. So, how did we try to solve the piece identification problem with the software side? We engraved markers into the pieces and implemented a marker recognition algorithm in our software. That way, users are sure that they have picked the correct piece. And the piece orientation and the sequence problems, how can we eliminate them? Well, we have made a 3D model of all the pieces, and we are showing with animation from what direction the users have to insert the pieces and connect them with each other. In order to improve the assembly experience and test new input methods, we implemented a gesture recognition. That way, the users can navigate through the software. Let's see a demo of our software. I will hand over to Krishna and Dennis.
Hello everyone, this is Krishna. Hi Krishna. Today Krishna will be using our software to construct his freshly delivered FabScan, and he is eager to do that. First, when he opens the software, he sees the main view in the middle. He understands that this shows him what he is constructing right now, and this is basically what he's going to see during his assembly process. After that, he discovers the left navigation bar. While scrolling to this bar, he sees that they consist of groups, and he may think that groups are a logical decomposition of the project you're going to build. So those are pieces you have to construct in order to construct your final project. And now he wants to start to build the group, and he chooses one that he wants, which is the motor holder group. But before beginning the assembly, he wants to know more about this group. He goes to the information button and sees an overview. Krishna sees that on the left side, he's displayed all images that are necessary to construct this group. Real-life images make it easier for him to find them in his environment. On the right side, he sees how it looks like when it's done, and an optional description about what it can be used for or which screws you might need to build it. As you have seen, there were many similar parts, and Krishna is not sure which one he should take to begin with. The current part is shown in the upper right, but still he may be confused. However, he sees there's a camera and tries to show the software the pieces, and maybe the software will help him. Well, maybe show another piece. Wrong one. Oh, so software says that this is not the correct piece. And let's try another one. Success! Now Krishna can proceed to the next step. You have seen two things happening right now. First, there was an animation. This animation may be important for the user to keep track of how his model is rotated and to not have a logical leap as they were in two different images. Also, there was an insertion animation which shows him how the new piece should be inserted in the previous one. In addition, at the top appeared a hint. Hints show important things which a user should consider. Krishna reads the hint and now knows that markers should always point to the inside. This will help him further to orientate his pieces correctly. As Krishna combines the pieces, he goes to the next step. Small hints sometimes also appear at the bottom, because maybe Krishna won't see them at the top. And now, if he wants to know more about how he should insert it, he can interact with the main view. He uses the mouse to rotate the model, and maybe he can then see for more complicated models how he should insert the pieces. If he wants to go back to the recommended optional default view, he can do so by clicking the respective button. You can also see the insertion animation again, if he desires to. So now we let Krishna finish this group by looking at the next steps. As Krishna has done with this group, he sees a big piece of MDF lying around on his workspace, but he's not sure to which group it belongs. He will try to use the voice recognition function together with the marker recognition to go to the correct group and start assembling the group which this piece belongs to.
Switch to group.
As the pieces necessary for this group are large, he has to change his workspace where he has more space. Unfortunately, now he will be not able to use his usual interface, which are keyboard and mouse. Instead, he will try using alternative interaction techniques, which are gestures using the Kinect and speech recognition. So he notices that above the camera view there is a hand button. He understands that if it's red, this means the Kinect can track his hand. If it's green. And if it's red, this means his hand is not visible and he has to do something in order to show it to the Kinect. Once his hand is being tracked correctly, he can use gestures to go to the next step. He sees an arrow at the top and reads it. Now he's again reminded of some important things. For example, that he has to screw with not too much force, or that the markers always point to the inside. Once he's done with this step, he proceeds to the next one. He tries to do this what is told to him, but he realizes that he made a mistake in the previous step. So he has to go back and see it again what he has done incorrectly. So you can use both hands if you want to. Well, I guess Krishna now knows what was his mistake and he can correct it easily. During his process of inserting grooves or his screwing process, we can tell you about why we use different diffraction techniques. We think they help you to adapt to your work environment. If it's a noisy environment, you might not want to use voice recognition. And if it's an environment where people are passing by behind you, you might not want to use the Kinect, as there are other people who might be tracked. So you have to choose which one depending on your situation. As Krishna goes to the next step, he wants to avoid the same mistake he did before by looking more carefully at the model. To rotate the model, this time he has to use gestures. To this he may gain more insight about the correct assembly, and before he does it, he wants to see it from the default view again. Therefore he has to use voice recognition again.
Reset view. Reset view. Reset view.
Now he can complete building this group. Of course, there are still, the system might be not that error prone, but we expect that in future Kinect quality will also improve, and then we will have even better results. Unfortunately, not everything can be explained in means of models. Sometimes for complicated tasks, we have to use videos. Therefore, we are allowed to use videos as steps, and they're treated as such. You can go to the previous video and to the next video, and their videos are small snippets which show only the most important things. This example, for the FabScan, you have to buy an assembled Logitech camera. You have to disassemble it and to do stuff that people won't understand without seeing a video. Let's look at the fifth video, for example. In the beginning, we show most important information, and then you will see that how things should be done. Watch carefully, as we have labeled this video, the hand of God. Okay. Now Krishna wants to finish building his FabScan. So he jumps to the last group. In this group, single pieces consist of previously built groups. Krishna steps to this just to see what will expect him. But while he does that, he realizes that he is an advanced user and he does not need this step-by-step animation anymore and the step-by-step support. So he decides to change the speed in which he is supported to expert mode. In expert mode, you have no animations and multiple items occur at once. He goes back to the FabScan to complete his assembly. The idea behind this mode is that an advanced user will be able to keep track of multiple items and to identify them without any problems. And as he keeps adding more and more pieces, the FabScan comes into its final form. Only one step left to finish everything. Success! Krishna is done with building the entire FabScan. What you have seen is a software customized to help you assemble the FabScan. However, if you want to, it's kept highly modular and you can provide a 3D model with optional images in an XML format and use the software to guide users to building your own project, post-fabrication project. If you fancy it, you can even add more things as insertion vectors or default view vectors to give your users even more support. Thanks for sharing this experience with Krishna and me. And now back to Kostas to see the evaluation of our software.
So let's find out how our software did in the evaluation. We asked 10 users to assemble the cube using the interactive system. 3 of them used the Kinect, and 7 users to do it using the web manual. And we tried to count the amount of errors that they did while assembling it. We normalized the results, and as we can see, using the interactive system, users did much less mistakes. The amount of sequence errors, the amount of identification errors also got reduced a lot. Unfortunately, the warning errors did not get reduced a lot. With warning errors, we mean the errors that the user does and can only avoid if he takes notice of a warning or a hint that he is given. This may be due to the fact that 80% of the users completely ignored the warnings until we told them to. We have changed the design of the warnings in our newest version of the software, and we think that that way more of them will take notice of them. So, what about the time that they need in order to build the cube? Well, as we can see, using the interactive system, users need much less time in order to build the FabScan. What about if they use the Kinect? Because this is an interesting question. Are gestures a viable solution in interactive assembly systems? Despite the limitations during the user studies, and despite the fact that this is a new technology, and there are some errors in it, we can see that the time that they needed in order to assemble it using the interactive system with Kinect and without keyboard or mouse was still much less than if they had used the web manual. This shows that this kind of input method can be applied in this kind of systems. We also summarize the comments that the users did while they were assembling the system. On the left, we have written down the comments that they did while they were assembling it using the web manual, and in the right, while they were doing it with the interactive system. We have highlighted the negative comments with red and the positive comments with green. So for the web manual, users said that they are not satisfied with the images, with the static images, and they needed more detail in order to find out what they have to do. What did they say about the interactive systems? Well, they said that it's good that the system shows what piece they are using currently. We are highlighting the piece with the green color to make it easier to notice what they are using. They also said that animations are very useful to see what they have to do. This comment is my favorite one. One user said, "When I need to build something complex, I usually Google it. But with this system, you do not need to check anywhere else. So I guess we beat Google." So, what did we do in the hardware design? We applied many modifications in order to solve the piece identification, the piece orientation, the sequence problems. We have abstracted and generalized the solutions that we applied, and we have made 4 patterns for it. Those patterns can be also used in other person-fabricated objects to solve similar problems. With our software, we show that integrating new input methods in interactive assembly instructions can be meaningful, since it opens new possible scenarios where this can be used. We have also shown that interactive assembly instructions have the potential to greatly improve the assembly experience and reduce the assembling time. For our future work, we would like to further polish the gesture recognition and the speech recognition, and we are also thinking of making a new warning system so that users take notice better of them. Thank you for your attention.